to help motivate the idea that we can use templates or models to represent different kinds of experiments and different kinds of sample spaces all at once using just one model, one kind of distribution that we can apply over and over again, let's think about the three following experiments. So think about flipping a fair coin where you can get heads or tails, and we observe the side it lands on. What about rolling a fair die or a balanced die and observing the side that it lands on? Or a simple random selection of one person from a sample of 10 people. What do all three of these random processes have in common? What they have in common is what we call the principle of equally likely outcomes. So, each simple outcome has the same probability as all the others. So we can think of this as a sample space that has n outcomes. The first one has 2 heads and tails. For the balanced die, we have 6 for 6 sides. And from the simple random selection of 1 from 10 people, we have 10. But each one is equally likely to be drawn. So the probability of each outcome, where we write x being that outcome, is 1 over n. And what is so special about this, for x being anywhere between 1, 2, 3, we're going to label these items. So for instance, in the example of rolling a die, we have the 6 sides labeled in terms of we represent them using this random variable that ranges from 1 to 6. And so each outcome has a 1/6 chance of happening. And this model of assigning this probability mass function of 1 over n for each value is what we call the discrete uniform distribution with parameter n. So the parameter is something that sets this model apart from other models of the same type, right? So it specifies the specific or the exact shape or the exact spread of the probability distribution. So, like we mentioned, for these different examples, they're all going to have the same fundamental characteristics. For instance, for the random selection of 1 out of 10 people, right, we have 1, 2, 4, 5, 6, 7, 8, 9, 10. So we take those 10 people, label them from 1 to 10, and the random selection of one of those people means that we land on, x equals 6. And each one has the same likelihood of happening. So we're right when we're representing the probability distribution graph. We get these vertical bars that all have the same height. So each one is 1 over 10, which we can write as a decimal number, that's fine. 1/10 here. And you should check then that it makes sense that if we add up all the outcomes, so from k equals 1 to 10 of 1 over k, sorry, not 1 over k, 1 over n, which is 1 over 10. So 1/10 added to itself 10 times, that does equal 1. This is a valid probability distribution. And so for each of the 3 scenarios that we had, we have a discrete uniform distribution, which I'll annotate, I'll abbreviate it as disc uniform, with n equals 2, so 1/2 and 1/2 for heads and tails. The second example with rolling a die has n equals 6, and the last one is a discrete uniform distribution that we have graphed up here with n equals 10. And so that also tells us automatically the probability mass function. So 1/2, 1/6, and 1/10. And we can infer different kinds of questions about probability and calculate specific probabilities, such as so in the example of, so for the random selection example, what's the probability of selecting someone who's indexed 7 or higher? Then you're just taking 7, 8, and 9 and adding those probabilities together. But since they're all the same, it's the same as just taking the number of outcomes, so 4, times the probability of each one, right, which is 1 over 10. And that's 4/10, or 0.4. And we can do that for all of these different kinds of probability distributions where we are representing all possible probabilities in this graph or using a table.